Hello everyone. Today we'll be covering a problem from a recent Code Forces round. I wanted to share this problem because I really like the solution. The question has quite a few levels of depth and it was really satisfying to be able to solve it. So without further ado, let us take a look at the problem. You are given an n by n matrix of integers. You can perform as many times as you wish operations of the following form. Pick an integer k and swap row k with column k. So for example, if I pick k equals 3 here, the row becomes the column and the column becomes the row. So we are supposed to find the lexicographically smallest matrix you can obtain, given that you are allowed to perform such operations as many times as you wish. And in the question, it is specified that to compare two matrices to determine the lexicographic order, you will compare row first. So you first compare this entry, then in case of tie, you break tie by comparing this next entry, then this entry, then this entry, then this entry, this entry, this entry, this entry, and so on. So for the limits of the question, n is at most 10 to the 3, and the matrix entries are at most 10 to the 9. So quite clearly, the matrix entry shouldn't really play a role in the algorithm. And instead, we are probably looking for something like O(n) square. Okay, so let's take a look at the solution. But before that, let's think about why this problem seems non-trivial. So it's non-trivial because actually you can implement the swapping as many times as you want. Can swap this, can swap that, can swap this, can swap this, and the order seems to be another degree of freedom as well. And it is not quite clear how the behavior of the matrix will be after performing all these swaps because this cross swap is quite unintuitive. So to help simplify the solution, we first have to make a few key observations. So here is a representative illustrative matrix, and the first observation to make is that the diagonals cannot be moved. So indeed, if let's say we are looking at the entry 3, 3, then you might think, okay, what happens if I pick k equals 3? Well, the row becomes the column and vice versa, but the diagonal turns out to be a pivot point that is stuck. And of course, you can try looking at other case and it will not even affect this diagonal entry at all. So this is a first simplifying observation. The diagonal, it is what it is. It cannot be moved. But how about the off-diagonal terms? Where can it possibly go? Well, firstly, a off-diagonal term like aij can only be moved by picking k equals I or k equals j. So for example, in this blue dot, it can move if you pick, let's say, k equals 2 and you swap the row and column. Or you can pick k equals 4, which will also swap the row and column and move the blue dot. And you notice that in either case, the blue dot will actually move to the green spot. So aij will swap to the spot aji, and then if you do a similar swapping again, you'll go back to aij. So now we know that each off-diagonal term aij can either end up back to where it is or swap with aji. And actually we know even more. If we specify let sk be the number of times the pivot k is picked, then we know that actually aij will stay where it is if si plus sj is an even number because you swap over and you swap back. Whereas if si plus sj is an odd number, then in the final configuration, it will end up being swapped over to aji. And this is a very powerful observation because there's two more corollaries from this. Firstly, the order in which you pick the pivots do not matter. Ultimately, you just need to count how many times I is picked, how many times j is picked, and you will know whether the blue number is now at the green spot or still back at its original spot. And secondly, the second corollary is that we can restrict sk to be the choice between 0 and 1 because everything is mod 2. You perform the operation 2 times, you are back to the original spot, right? So this question becomes determining for each pivot whether we activate it or not activate it. And the order again doesn't matter. So this is a great simplification. So now we come to the question of do we activate the pivot or not activate? And to do this, we need to think about should we make the blue spot and the green spot swap or not swap. Now, if we want a lexicographically smaller matrix, ignoring all the other gray spots for now, well, if blue is less than green, we would love to keep blue where it is, because in the lexicographic order, anything in the upper right triangle will be hit first before its corresponding partner in the bottom left. So if blue is less than green, we want to keep where it is, which means we will like Si and Sj to be equal. They are either both 0 or both 1. On the other hand, if green is less than blue, we will love Si and Sj to be opposite of each other. And of course, if green equals blue, then there is no additional constraint or no additional preference. Okay, so but this is only for the pair blue and green. We have all these different pairs, all these off-diagonal pairs. So the question is, are we sure the preferences don't contradict? Well, they may actually end up contradicting each other. So we do need some form of prioritization, because each pair will give a constraint on two of the dots, right? And it may not be possible to satisfy all preferences. So we need to prioritize, and the way we prioritize is we will want to look at the off-diagonal terms that are considered first in the lexicographic order and prevent any contradiction. How do we actually implement this? Well, what we can do is we can implement a disjoint set union structure to figure out which constraints to actually implement and which constraint we have to forego. So what we do is we have one point for each of the values S1, S1, S2, S3, and so on. And we will draw an edge, right? If there's a constraint between Si and Sj, and the edge can either be a edge that says they must be equal or an edge that says that they must be different. Then no edge means there's no constraint imposed. So what we do is we start with the off-diagonal term that matters the most first, which is A12, and compare the blue and green. Then we can see, okay, between S1 and S2, should it be the same or different? And then we look at the next off-diagonal term that matters the most next and see whether between S1 and S3, should it be the same or should it be different? Not forgetting that it could also be no preference. And so on and so forth. So we go down the order of priority. And whenever we find that a constraint is being implemented between two parts of the disjoint set union that are actually belonging to the same set, then we do not add that constraint, because let's say we go down and then now we are at S2, S3, and we say, should we add a constraint? No, we shouldn't, because it might either end up contradicting the existing constraints, or it is already going to be consistent with the existing constraints. So we can see that this disjoint set union will come in handy here. You can very quickly check whether the constraint I'm going to adding is between two stars that are in the same set or in different sets. So if you go through all the order n square of off-diagonal pairs, we'll end up with a forest of trees eventually. And then with this forest of trees, we can actually figure out now whether to assign 0 or 1 to each Si. So for each tree, we do a BFS or DFS to assign the allocation in 0, 1. So specifically, you select a tree, right? And the first assignment to the tree does not matter, because actually if you flip everything on the tree, the constraints will still be satisfied. So the very first vertex without loss of generality can assign anything. And then based on using BFS and DFS and the conditions specified by the edges, you know how to deduce the value for the remaining SIs. So after having done this, we'll have allocated the best possible values of Si for each I. And so now we can print the answer. So for each ij of the matrix, what is the final entry that we want? It will be, well, you check Si plus Sj to decide whether to print Aij or Aji. So that's really all to the problem. I find it really interesting because the concept using the disjoint set union did not really come in until much later, after you make all the simplifying assumptions, and then there's now a data structure that is involved, and then after that you still need to do BFS and DFS. So quite an interesting problem that uses a few techniques from different areas of competitive programming. So hope you enjoy this problem. Stay tuned to the channel for more videos and see you soon.